heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world.
All right, good evening, everyone, and welcome to Mount Washington Observatory's Science in the Mountains lecture series. My name is Brian Fitzgerald, and I'm the Director of Education here at Mount Washington Observatory. And joining us this evening to tell us all about what makes the Gulf of Maine so unique and how it's responding to climate change from the Gulf of Maine Research Institute is sea level rise scientist Dr. Hannah Baranes. Thanks so much for joining us tonight for Science in the Mountains. Happy to have you with us here tonight. If you're not already familiar with Mount Washington Observatory, we are a private, nonprofit, member-supported institution with a mission to advance the understanding of the forces that create Earth's weather and climate. And the way that we accomplish that is through operating our summit-based weather station with around-the-clock weather observation and forecasting, by conducting research and product testing projects, and by developing and offering innovative educational programs. If you have questions for tonight's speaker and you're joining us on Zoom, please make sure you use the Q&A button. You can find that right at the bottom of your Zoom toolbar there. Make sure you get your questions in whenever they pop up. We'll make sure that we'll leave time at the end of this program to get to as many questions as possible. If you're joining us on Facebook, welcome. Thanks so much for joining us there. We won't be able to respond to your questions in real time. However, we'll certainly have our summit staff respond as quickly as possible following the program this evening. If you'd like to connect on Zoom for our next program, make sure you register over at mountwashington.org/SITM. Alrighty, well, before we get to tonight's presentation, we have a quick poll for those of you who are joining us on Zoom, and I'll launch that poll here in just 1 second. In fact, you should be seeing it pop onto your screen now. Got some great questions tonight, including a few from this evening's speaker. Our first question here, always curious for those of you joining us on Zoom here, well, maybe this is your first program, but we're curious how many Science in the Mountains programs you've joined previously. Maybe it's your first, maybe you've joined a few, maybe more than 10, maybe you've been along the ride here for most of these virtual programs over the last 2+ years. Always curious. Next question here comes from our speaker. The main reason I came to this program is A, I'm worried about climate change and want to learn more. B, I'm curious about why tides, sea level rise, and/or warming are unique in the Gulf of Maine. Perhaps it's both A and B, or perhaps it's C, it's something else. Another question here. The tide range in the Bay of Fundy can reach what? 10 feet or 3 meters, 25 feet, or 7.6 meters, or 50 feet, almost 16 meters. And then finally, the two main sources of uncertainty in predicting future sea level rise are human emissions and the impact of ocean warming, human emissions and the instabilities in the Antarctic ice sheet, or is it mountain glacier melting and changes in ocean currents? Some good questions, some toughies from our speaker this evening, who will be getting to a number of these answers tonight. So I'll give you just a few more seconds to respond. It looks like more than 3/4 of you have already done that. And we'll end the poll in just a few seconds here in 3, 2, 1. Alrighty, we'll end it right there and we'll share some results with everybody. Well, it looks like, wow, quite the mix here. Half of you have joined us before, between 10 and 2 programs. More than 1/4 of you, 38 individuals. It's your very first program this evening. Hey, welcome. Thanks so much for joining the Observatory Science in the Mountains program. Hopefully you'll join us for another program here in the future. And if you've missed some others, you can always see our recordings on our YouTube page or over at mountwashington.org. And then, wow, special shout out to those of you, 10% of you think you've been to all or nearly all the programs. Thanks so much for continuing to join along. As I was just telling our speaker a little bit earlier, this is one of my favorite programs because basically we just get to hear from really interesting people all about the great work that they're doing. And tonight's program should be no exception. All right, the main reason why I came to this program, more than half of you are well, both worried, but also curious. And that's a great thing. And for some of you, hey, it's another reason altogether that you came to tonight's program. Glad that all of you can join. And then for our two trivia questions here, the tide range of the Bay of Fundy, most of you thought it was that highest level, 50 feet of change in the tides. And then lastly, the two main sources of uncertainty in predicting future sea level rise, a little more of a split here, but the winner overall, human emissions and instabilities in the Antarctic ice sheet took the prize here. So we'll just have to wait and see. I do have the answers here, but I'd rather hear them directly from our speaker. So without further ado, I'd love to introduce Hannah this evening. Hannah, I don't know if you can see and hear me, but love to welcome you to the program and love to hear all about your work tonight.
Hello, everybody. Thanks for having me, Brian.
Yeah, well, I can hear and see you just fine. So by all means, take it away.
All right, I'm going to share my screen. Okay, and Brian, maybe pop back on if something is not working, but if I don't hear anything, I'll assume we're good.
It looks great. Go for it.
Okay, great. Okay, so hello, everybody. My name is Hannah Baranes. I'm a scientist at the Gulf of Maine Research Institute. Thanks for having me, Brian, and thanks so much to all of you for taking some time out of your nights to learn about the Gulf of Maine. So for those of us who live in the northeastern US or along the Gulf of Maine coast in Canada, we live next to this really unique part of the world ocean. And in digging into sort of these features that make the Gulf of Maine so unique, you unearth these fundamental physical processes that govern how the world works. And these are the ones that really kind of motivated me to become a scientist. So I'm excited to share all of that with you. And thanks again for being here. So before we dive in, I'm just going to tell you a little bit about what Gulf of Maine Research Institute is and what I do there. So we're located in Portland, Maine. We're a nonprofit research institute, and our mission is to deliver collaborative solutions to global ocean challenges. And depending on who you are at GMRI, that looks different. So we have researchers working on problems like developing climate-informed stock assessments for fisheries. We have people who work with communities to deliver technical assistance to fishermen. And we have educators who actually bring over half of Maine's fifth graders through our building every year to do a hands-on lab learning experience. And I joined GMRI in January and started our Coastal Hazards and Sea Level Rise lab. So my goal is to develop localized flood projections that can be used for community scale planning along Maine's open coast and estuaries. So what that all means, we have pretty good regional scale information about what's going to happen in terms of future flooding. But when it comes to being in a specific community and saying this bridge is going to be at a 50% chance risk of flooding in 2040. That's the kind of information we're really looking to develop. And as a flavor for the types of projects I work on, actually, let me just turn on my pointer here. I'm working on developing sort of transferable and scalable methods for doing flood hazard assessment on working waterfront. I'm piloting some new tide gauge technologies in communities and pairing them with community science programs so that you can both get more accurate tide predictions and tie them to local impacts so that you can develop a sort of system of local flood thresholds and alerts. And then on really fun days, I get to go out to the beach with elementary school Mainers and teach them what tides are. So each day looks different and it's a really fun place to work. And last thing before we dive in, I just want to acknowledge that talking about sea level rise and ocean warming can be a bit of a heavy topic. And kind of in addition to the frustration and sadness I feel around climate change, there's this second climate change lens I've developed through my work. And that's that in trying to come up with local climate change solutions, there's this opportunity to really think about what can we do to help coastal communities thrive in the future. And that might look like making fisheries more sustainable or improving coastal ecological health, doing more STEM education for kids, or just being equitable and just in all the decisions we make. So yes, there's a lot of negative things that come along with climate change, but I also kind of derive a lot of, I'd say, optimism and hope from my work. So with that, let's jump in. So the 3 questions I sort of posed to you in the talk teaser, if you remember reading it, whatever you did. Why does the Gulf of Maine have the biggest tides in the world? Why is the Gulf of Maine warming 3 times faster and experiencing sea level rise rates 1.5 times faster than the global ocean average? And why were we hit with 2 record-breaking floods in a single winter in 2018? These were 2 nor'easters that hit in January and March. And for those of you in particular who live along the Massachusetts coast, you probably remember them. So let's start with tides. And here's one of my favorite pictures from Eastport, Maine, up on the Maine-Canada border, where the tide range is 6 meters or about 20 feet. But it does get bigger than that if you go farther to the northeast in the Bay of Fundy. So if you've never gotten to learn about tides or haven't gotten to think about them in a while, I'll sort of do a primer on water levels, tides, and tide prediction. So the water level we observe at any location along the coast is actually the sum of a bunch of different components. So if you think about a graph, or I'll show you a graph of water level through time, there's whatever mean sea level is doing. And then you have water levels going up and down from gravitational forces among the Earth, the Moon, and the Sun. Those are called tides, or we often call it predicted water level because we can predict tides, and we'll get into that in a moment. And then the water level we actually observe deviates a bit from the predicted tide because of weather. And here I've just highlighted an example where the observed water level might be higher than the predicted because of a storm. And that difference in predicted and observed is what we call storm surge. So here's sort of a little graphic of what how the moon influenced tides. So here you're looking at a diagram of the Earth, and the blue is the ocean being kind of stretched out like a skin on 2 different sides, on the side facing the moon and the side that is opposite the moon. So it's a gravitational force that's pulling up the ocean towards the moon. Gravity is just attraction between any 2 objects with mass. And then on the opposite side, water is getting pulled up because of a centrifugal force. And that you can just think of grabbing hands with somebody, swinging in a circle, and you kind of feel this outward pull. And that's what's happening to the ocean opposite the moon. So now imagine you're kind of at this point on Earth, and we're going to spin counterclockwise once in a day. We're going to be at low tide. When we're facing out of the screen, we'll face the moon, be at a high tide. We go into the screen, low tide, other side, on the left side of your screen, high tide. So every day we spin through, where we are in the Gulf of Maine, we spin through 2 high tides and 2 low tides. In reality, it's quite a bit more complicated than that because there are also forces from the sun, and we have continents that get in the way of these tidal bulges. We have friction, and the rotation of the Earth also influences the way tide behaves. But generally, this is the gist of things. So I mentioned we can predict tides. So if just this were going on, what's in the diagram with the Earth and the moon, we would have water level going up and down every 12.4 hours. But there's also a whole bunch of other processes. So for example, we have the moon orbiting the Earth every 27.6 days. That would be another wiggle. The moon's orbital plane spins around every 18.6 years. That's another wiggle. And I think that to model the tides in any one place, usually you're modeling upwards of like 30, 40 of these wiggles. So tides are really just a sum of a bunch of wiggles. The way we predict them is we sort of go into one of these water, sort of a time series of water level, and we just start subtracting out the wiggles that we know sort of how frequently they oscillate, until you basically account for everything you're observing. And then when you want to predict the tides, you take all those wiggles and you add them back together, and that's how you get tide predictions. So there's this great video on YouTube. If you've got 10, 15 minutes, I kind of forget how long it is. I recommend watching the whole thing about, let's see, I think I got to get rid of my laser pointer to play it. I recommend watching the whole thing, but this just sort of is a nice little visual of what that tide prediction looks like. So there's a water level signal. We're pulling all the wiggles out of it from known sun, moon, earth forces. And then when we want to get, oops, let's see. And then when we want to get tide predictions, we just add them all back together. All right. So now these days I can do that on my computer, but back in the day before computers, we had essentially analog adders of wiggles. So each of these little rotating things represents one of those sort of forces, tide generating forces I talked about. And this machine just has those things spin and it adds them all together into a tide signal. And again, that video gets a little bit more into how these things work. All right, so what you really wanted to know is why Gulf of Maine's tides are so large. And the answer to that question is indeed that tides can reach 16 meters all the way up in these northeastern embayments of the Bay of Fundy. So the Bay of Fundy, to some extent, does sort of like funnel tides and pile up water, but also imagine the Gulf of Maine as a bathtub. So if you were to sort of pick up the water on one side of the bathtub, sort of the way the moon pulls water away from the earth, and then release the force, you'd get water sloshing back and forth and back and forth. That's called a seiche, which is maybe something you've heard of in the Great Lakes with storms. So anyhow, how long it takes for that slosh to go back and forth depends on the size of your bathtub. In a small bathtub, it takes a couple seconds. In the Gulf of Maine, it takes about 13 hours. And like we mentioned before, the main tide producing force in the Gulf of Maine is that diagram I showed you. It's the Earth spinning relative to the moon and going through one of those tidal bulges every 12.4 hours. So kind of imagine a kid on a swing. So you have a kid on a swing going back and forth every 13 hours, and it's sort of the tides are kind of like giving it a push at almost exactly the right time just to amplify the tides. All right, check. That's why we have the largest tides in the world. Next, let's talk about why we were hit with 2 record-breaking floods in one winter in 2018. So there is a tide gauge or a water level measuring device sitting in Boston Harbor, and it's been out there recording water levels for, I think, 102 or either 100 or 102 years now. I forget which one is Portland, which one's Boston. But in that roughly 100 years, the 2 water levels we observed from the January and March nor'easters were the first and third highest ever recorded in 100 years, same winter. And that might kind of like make sense at first because sea level's rising, so we'd expect to be seeing higher water levels more towards the present. But if you get rid of the water level trend, so basically you adjust everything to the same sea level, their ranks just drop to number 2 and number 3, and they're beat out by the blizzard of 1978. So I found myself kind of wondering after these 2 events happened, I was in grad school at the time, like, what is going on here? Did we really have this sort of wild coincidence just in one year? And it turns out, so how high the high tide is when a storm hits in the Gulf of Maine is really the primary control on flood severity. So this is the, I'll turn my pointer back on. So this is the NOAA tide gauge data from Boston Harbor during that January nor'easter, which is that highest water level ever recorded. So the blue is the predicted tide, and the green is what we actually measured during that event. And this black dash line is showing you the height of the average high tide in Boston. So if you look at the water level increase above the average high tide, roughly half of it is just from the tide being higher than average. And then the other half of it is from the actual storm surge itself. And if you look at this storm surge, I think I found that it was like, as of 2021, it was the 79th highest storm surge ever recorded at the tide gauge. So a pretty unspectacular storm leading to record-breaking water levels just because of the tide it happened to align with. And so it turns out the height of high tide varies naturally over days, months, and years. And again, that's just because of all those wiggles we talked about when we were going through tide prediction. And one of them that has a really big effect in the Gulf of Maine is called the lunar nodal cycle, and it causes the tide range to get bigger and smaller every 18.6 years. So high tides are higher than average for about a decade, and then they're lower than average for about a decade. And it just keeps flipping back and forth. And in 2018, we were at the peak of this cycle with higher than average tides. And if you look back over 200 years at the top 10 flooding events ever to impact Boston, 8 of those 10 occurred during peaks of this lunar nodal cycle. And the impact of this nodal cycle on flooding got some serious press in the New York Times actually about a year ago. I think this is an article from maybe July 2021. They call it the moon wobble. So how the moon wobble affects rising tides. And I thought this was awesome. NASA tries to reassure the public there is nothing new or dangerous about the wobble. And now you know why. So the reason this is important is it helps when we think about tide risk or flood risk going into the future. There are some years where it's going to be worse and some years where it's going to be not as bad because of predictable variation in tides. So taking the January 2018 flood as an example, depending on the year that storm had happened in, it could have had a 0.5% chance of occurring, or it could have been 4 times more likely with a 2% chance if the tides had been higher than average. And in 2018, it happened to have a 1.4% chance. And figuring out how to calculate those numbers is 2 years of a PhD. So it all can just boil down to 2 little sentences. All right. The one thing I'll add about that is that's kind of something I'm still, that's what brought me in part to Gulf of Maine Research Institute, is getting to and trying to develop these really localized flood hazard assessments, trying to really account for the outsized impact that tides have on flood hazard. And that's all sort of like pretty new to the modeling and statistics world and trying to calculate flood hazard. Okay, last one. Let's talk about why the Gulf of Maine is warming 3 times faster and experiencing sea level rise rates 1.5 times faster than the global average. So sea level has risen about 7 inches in the last century, but 5 of those inches have occurred since 1970. So we're experiencing pretty significant acceleration. And so far, most of the sea level rise we've seen has come from melting mountain glaciers and thermal expansion. So that's just as water heats up, the molecules move faster, it takes up more space, and that causes sea levels to rise. And so far, we've seen relatively less sea level rise from Greenland and Antarctica, which are the big ice sheets that sit at the north and south poles. So the blue is showing sea level rise in the northeast, and it's been quite a bit faster historically than the global average. And that's for a few reasons. So first, the Gulf of Maine coast is subsiding or sinking as the land surface adjusts from the last ice age. So 20,000 years ago, there was a big ice sheet sitting over North America. You can picture it as this balloon, and the land underneath the ice sheet was lower, but land around the ice sheet, sort of at its margins, was sitting up on a bulge, and that's shown in cross section here. So the Gulf of Maine was roughly kind of sitting where I have this red circle. Ice sheet melts, and once that load is lifted, the crust starts to adjust to the way it was before that load was put on it. So today we're sinking. I think in the southern Gulf of Maine, the sinking is happening about 0.8 millimeters a year, and it's about half that kind of as you get towards northern Maine. And for reference, rates of the global rate of sea level rise is 4-ish millimeters a year. So it's pretty significant. Changes in currents are also causing faster rates of sea level rise in the Gulf of Maine. So the ocean surface actually has topography caused by currents and tides. So if you look at the Gulf of Maine, or just the northwestern Atlantic up here, the boundary between, blue is showing areas where the sea surface is lower, and red areas are the sea surface is higher. So this boundary between the blue and the red in the northwestern Atlantic is the Gulf Stream. So it's this fast-moving current that's carrying warm water from low latitudes where it's warm to higher latitudes where it's colder. As the Gulf Stream turns eastward, it pulls water away from the Atlantic coast. And we're going to get into this more in a little bit because it's connected to warming, but the Gulf Stream is slowing down. So that's pulling less water away from the coast. You can kind of think about sea level as like sloshing back up towards the northeastern US. And again, I think in just one more slide, I'll revisit the Gulf Stream slowing down and warming. So this is a map just showing kind of variations in the rates of sea level rise just along the US coastline. And it varies quite a lot. So we already talked about rates being faster than average in the Gulf of Maine. The fastest rates in the US are in the Gulf of Mexico, more than double the global average. And that's because we're extracting oil and water from soft sediment. For example, in the Mississippi River Delta, that's now just compacting under its own weight as we remove the fluids that create pressure that makes that ground stable. In the west, we've been experiencing slower than average rates of sea level rise. Sea level is actually dropping along the Alaska coast because land is rising from plate tectonic motion. And then this atmospheric cycle called the Pacific Decadal Oscillation has been causing lower rates of sea level rise in California. That cycle is flipping now, and rates are have started to go up out there. Okay, back to ocean warming. So if this is something you're interested in, the Gulf of Maine Research Institute puts out annual and quarterly warming updates. So you can go to our website and check those out if you'd like to learn more, but I'll give a quick overview. And I just want to credit Kathy Mills, Adam Kemberling, and Dave Reed Miller, who are my colleagues who put these things together. They're really great. So this is showing, the black line is showing sea surface temperatures in the Gulf of Maine from the 1980s through 2021. So in 2021, the average sea surface temperature was 54.1 degrees Fahrenheit, which is about 4 degrees above the long-term average. This blue line is showing the warming trend, and the green line which is about 0.8 degrees Fahrenheit per decade. The green line is the global trend. And the important thing to note here is that the Gulf of Maine warming trend is about 3 times faster than that global ocean average trend. Okay, so why is this happening? Well, clearly it's simple. There are these kind of taglines that scientists like to put out all the time, and one of them is, it's an area of active research. That is truly the case for trying to kind of uncover the mystery of rapid Gulf of Maine warming, but we can dig a little bit into it. So just as a quick primer on Atlantic currents, oops, let's see, I just clicked something. Okay. So in the northern Atlantic, around around Greenland, there's really cold, salty water that is some of the densest ocean water on Earth that is at the surface and sinks. And that drives this sort of conveyor belt circulation of cold water sinking at northern latitudes, traveling south at depth, coming up to the surface, and then warm water coming back north. That's called the Atlantic Meridional Overturning Circulation, or AMOC, you also might have heard it called. And this sort of area, this orange line is the Gulf Stream that I pointed out on that sea surface topography slide. So, okay, I mentioned, actually, let me back up a second. So as ice melts, so for example, the Greenland ice sheets melt and glaciers in the northern hemisphere melt, that's dumping a bunch of fresh water into the North Atlantic. Fresh water is less dense than salty water, so it's slowing the formation of this really dense salty water that sinks and just slowing down this whole conveyor belt of circulation. And one piece of that slowing down, like I mentioned before, is the Gulf Stream slowing down and weakening. So if you think of the Gulf Stream like a hose that's on a jet setting, so sending this really sort of powerful stream out, and then you turn it down to a shower setting, the stream becomes a lot, or becomes wider. And that's what this image is showing. So this lighter orange color is a mapping of the Gulf Stream between 2000 and 2009. And then the slightly darker orange color, you can see it getting wider between 2010 and 2019. And so the impact of that is warm water essentially just leaking across this ocean slope and into the Gulf of Maine. There are a few other theories out there that I think in the interest of time, I will not get into, but some are related to natural climate variation and some are related to other human forcings. All right, so at GMRI, one of the main reasons we've cared about this for a long time, being researchers who are involved in the fisheries world, is that species like to live in certain temperature water, and decreases in cod and lobster productivity, which are both super important to Maine fishermen, have been linked to increases in temperature. And this is, again, work from a colleague, Kathy Mills at GMRI. But if you look at where lobster and black sea bass have lived from the x-axis is 1970, moving up to the present. The y-axis is showing the center of latitude of their populations. You can just see both species moving northward. Okay, so we've talked a bit about what is going on now, but with sea level, the discussion often turns to the question of how much will sea level rise? And we'll get a little bit into that as well as our last topic. Okay, don't worry about the axes here. It's not the point. I know they're hard to see. So this is showing various sea level rise scenarios going from the present out to 2150. And they're essentially saying that a really big range of futures is possible. And in those poll questions, I asked you what the major sources of uncertainty are in sea level projections. And I wanted to give you all sort of a sense for those and why things are looking so uncertain out towards 2150. So I mentioned that so far ice sheets have contributed relatively little to sea level rise. So 1.6 inches so far from Greenland and 0.2 inches from Antarctica. But these things are massive. Gosh, okay. my zoom is covering up the top Greenland number. I think it's 78 feet of sea level potential locked up in the Greenland ice sheet, but you can read the number, so maybe I'm wrong. And in Antarctica, there's 187 feet of potential sea level rise locked up in that ice. And the Antarctic ice sheet in particular, because most of it sits on bedrock that is below sea level, it's extremely sensitive to slight incremental increases in temperature that can trigger mechanisms that lead to physical instabilities and really rapid melting. And so the question is both the two questions are how much will we emit? So how much will temperature rise? And exactly when do these physical mechanisms of instability kick in and lead to rapid melting? And again, don't worry too much about the axes here. What these red lines, sort of just to illustrate this point, what these red lines are showing are the rates of sea level rise just from Antarctica, with 1.5 degrees of warming at the top. 1.5 degrees of warming is the Paris Agreement target that we often hear about in the news also. The middle is 2 degrees of warming and the bottom is 3 degrees of warming, where you see this really rapid acceleration in Antarctic ice sheet melting contributions to sea level rise. So this is just this quote kind of drives it home. These results demonstrate the possibility that rapid, unstoppable sea level rise from Antarctica will be triggered if Paris Agreement targets are exceeded. So again, that's where the focus on 1.5 and 2 degrees comes from within the sea level rise community. So in Maine, we have adopted official sea level planning targets based on a 2017 NOAA technical report that was just updated this year. And we have a legal mandate to incorporate these commit to manage scenarios into state agency regulations. And those targets are relative to the year 2000, 1.5 feet of sea level rise in 2050, and 4 feet of sea level rise in 2100. And I think that just thinking about these numbers, taking them at face value, like what does 1.5 feet or 4 feet of sea level rise really mean? What's the impact, especially given that in the Gulf of Maine, these numbers are pretty small relative to what our tide range is. So I think a good way to illustrate the impact is to think about it in terms of what it does to frequency of flooding just from tides, just from high tides. So without storms, just from high tides, we already get flooded a little over 3 days a year in Portland. If you increase sea level by 1.5 feet, this number jumps from 3 to about 1/3 of days a year we'll have a high tide that floods us. then in 2100, if we have sea level go up by 4 feet, we're experiencing high tide flooding pretty much every day. And when I first saw these numbers, or I guess maybe even calculated them, it was kind of mind-boggling to me that how could, I mean, this much sea level rise totally like change the character of a city we live in by flooding it every day. And I'll illustrate why that happens. So you all are now experts in knowing that the height of high tides varies naturally. And so you can think of the heights of those high tides being sort of distributed like a bell curve. So if you think of sort of, let's ignore different genders, but if you think of people's heights also being distributed like a bell curve, most people are about sort of an average height, and then you have a few people who are really tall and a few people who are really small. Same deal with tides, they're sort of distributed like a bell curve like this. So here,
Uh-oh, Hannah, it looks like we lost your audio for a second. Oh, now I hear you.
Hey, Brian, can you still hear me? I just got a note that my sound went off.
Yeah, it might have been your headset, but I can hear you okay now. Oh man, just when you're going to get into standard deviations and
If you
everything.
cannot hear me, I just switched to my computer mic. Hopefully that's all right. Sorry about that, everybody.
Yeah, no, I can hear you just fine. Go for it.
So here's that normal distribution or bell curve of high water heights. And this vertical line is basically showing you if you cross this height, you're going to get flooding. And under current conditions, only the sort of like tiny tip of the curve is crossing that high tide flooding threshold. But raising sea level is essentially like taking this whole bell curve and shifting it to the right. Okay, so if we do that, oh no, I also lost my ability to advance slides. Okay, there we go. All right, so if we shift it to the right, suddenly we get a much fatter part of this bell curve crossing the line, and we get a lot more high tide flooding events. And then we shift the bell curve a little more to the right, and everything falls to the right of that flooding threshold. So this is something that you'll sometimes maybe hear referred to as sea level rise leading to a big acceleration or a nonlinear acceleration in flooding events. Okay, we made it to the end despite the tech problems. So we talked about why the Gulf of Maine has the biggest tides in the world, why we're hit with 2 record-breaking storms, and why we're experiencing faster than average sea level rise rates and warming. Thanks so much again for your attention, and got plenty of time for questions.
All right, great. Thank you so much, Hannah. I really appreciate all that and for going with the flow there.
Oh, just a moment.
All right. Well, thanks, Hannah. For those of you who are joining us through Zoom, by all means, I already see some questions that have come in through the Q&A button there. By all means, if you're joining us on Zoom, make sure you get your questions in using that Q&A button here. Hannah, I know I have a few questions for you myself, but we'll get right to it if that works for you. And let me make sure I got my, oh, that would be nice. How about we do that view for everybody? All righty. So first, just a quick question from Anonymous here on that lunar cycle. The person's asking, where are we in 2022 in that cycle? Because 2018 was right near the peak, right?
Yeah, great question. So gosh, sometimes I don't get the years exactly right, but after 2018, we've come back down. So we're kind of in a lull in terms of the number of high tide flooding events we're experiencing. But towards, I think, sort of like the middle end of this decade, we're gonna hit the bottom and start to have the tide range get bigger again. And so when we get into that situation, you can sort of think about larger than average tide range adding to sea level rise, and those two combine to lead to sort of a more rapid acceleration in the number of flooding events we'll see compared to just having sea level rise alone. And then in the following decade, the decrease in tide range counteracts rising sea level, and you kind of get a plateau in flood hazard. So yeah, great question. We're sort of in the low end right now, but it's going to come back up.
Yeah, I mean, and certainly, I mean, as I picked up on before, and what I see even from our local forecast office in Gray, Maine, usually when those coastal flood advisories and things like that come out, usually there's pretty specific mentioning it's coinciding oftentimes a weather event with specifically the right timing with already naturally occurring high tide mark, right?
Yeah, yeah, right. Again, because the size of the tide is big compared to the storm surge. So yeah, that's super important. And one kind of interesting thing I didn't mention was that in the Gulf of Maine, the primary type of storm that causes severe flooding are winter storms or extratropical cyclones compared to tropical cyclones or hurricanes. And in part, that's because hurricanes are these really sort of fast, intense storms that cause a rapid rise in water level. So the duration of the storm surge is pretty short. And so whereas nor'easters are these big, slow moving things that lead to this prolonged surge. And so hurricanes, just because they're short, you're less likely to have surge intersecting with a high tide. And that was what happened during Hurricane Sandy. The storm surge was actually quite big in the Gulf of Maine, but it hit at low tide. So it didn't even reach the height of, I think, that day's high tide.
Oh, interesting. Thank you for that. And actually sort of, actually not so related here, but a question from Jack, it's a good one that made me curious about how seasonality maybe even plays into this as well. How does water temperature impact tides? So is it different, you know, in like the middle of winter or toward the end of, well, beginning of fall when the oceans are really warm? I mean, any differences there?
Yeah, so I'll answer the question in two ways, and hopefully one of them gets to it. So there is a seasonal cycle in water level, just caused mostly by prevailing winds and the locations of primary currents. But as the Gulf of Maine warms, what that changes is the way that the water is stratified, meaning like having warm, for example, like a thick layer of warm water sitting on top of cold water. And again, like tides are a wave. So that kind of stratification is friction that acts on the wave. And so as kind of the structure of the water column changes, it changes how waves and therefore tides move through the water. And that's an active area of research, and especially an especially interesting one in the Gulf of Maine, because we've observed tides getting slowly bigger over the last century.
Interesting. Yeah, it's a simple question, and something told me that was not going to make for a simple answer.
Can of worms.
For sure. Thank you. Another question here from Paul, who's curious. In one of the figures you had showed earlier, Paul's asking, what's the difference in height between the highest sea level that you were sort of showing out in the Pacific and the lowest sea level in the North Atlantic? I guess just for like reference or scale. Do you have any sense of that?
I don't know exact numbers, but it's on the order of feet.
Feet.
Mm-hmm.
Okay. Yeah, because I mean, even thinking those seasonal changes like, oh my goodness, Enzo and El Nina and La Nina cycles, and how much water is physically moving across like the ocean, and some of the differences in sea level height. I'm sure even in those circumstances, we're talking about the difference of maybe feet there as well.
For those, I think more like inches for those.
Oh, okay.
Mm-hmm. Yeah.
Oh, wow. All right. So that is actually significantly different.
Yeah.
Interesting.
Mm-hmm.
So Lisa asked a good question here, and one that I might even expand upon a little bit as well. So Lisa's curious, so what do you say to climate change deniers with the data that obviously your data that you look at specifically around Gulf of Maine intersects with global data, global trends, historical records? I'm just kind of curious, even from like a broader perspective. I mean, what's some of the, I guess, maybe general skepticism maybe your work is met with?
Gosh, maybe in part because of where I live, the place I most commonly run into skeptics are just like talking to family or talking to family, honestly, maybe. But Lisa, this is almost a non-answer to your question, but I think that with someone who is a climate denier, showing them more data is very rarely going to change their mind. And so the tactic I've tended to take is rather than showing data, sort of kind of approach conversations with them with curiosity, and maybe start by asking, well, sort of like, what's your end game here? What are you like when you think about climate, like what do you care about? And I think rather than sort of inundating them with, these are all the things that I want you to know about what the data say, I think kind of starting from a point of listening and trying to understand is more effective. Because I've tried to throw data at other people, and it's nothing but futile, I would say.
Yeah, I could understand that. That's really interesting. Thanks, Hannah. Here's another interesting question about temperature change in water from Pete. Pete's saying or asking, aren't ocean surface temperatures changing, but deep down they're not really changing a whole lot? What, I mean, again, this might be a little outside of maybe some of the work that you do, but what do you know potentially about this question?
That it's true, and that's most of what I know.
Yeah. Oh, interesting.
Yeah, because it's warming faster than it is at depths. So you can think of kind of everything, sort of all the pieces of the Earth system they take different amounts of time essentially to react to forcings. So if you suddenly like blast our atmosphere with a lot of heat, the whole thing will warm up fast. Whereas the ocean, it reacts a lot more slowly, and it mixes over much longer time scales. And so warming impacting the deep ocean takes longer than impacting the surface ocean.
Yeah, that makes sense. Here's a great question from Allison, who says, you talked about the impact of cod and lobsters, but is there any direct impact to land, say, for example, increases in coastal erosion or indirect impacts to coastal flooding from storms?
Yes, definitely. Coastal erosion, storms move soft sediment around, and we have a lot of soft sediment at the coast. And then I think an increasing number of flooding events often, kind of in addition to the damage we get from extreme storms, the more routine flooding we get from these sort of high tide flooding days. In Maine in particular, we have a lot of communities that are only accessible by like a single bridge or road, for example. And when those flood, you can just like really cut off entire segments of a community. And I think that and then impacts to sort of all the underground infrastructure we can't see, like septic systems and utilities. Those are the things that I tend to think about first. I hope I answered your question, because there's a lot to unpack.
No, yeah, exactly. And I feel like maybe, correct me if I'm wrong, I felt like maybe we had connected another time we were talking about just, I mean, also the nature of New England's coastline and sort of the geology of New England's coastline is complex itself. So there are some pockets that seem to be particularly prone to either some sort of erosion, whereas others, well, they might still be vulnerable to sea level rise and flooding, but maybe the erosion and things like that aren't quite as concerning.
Yeah, and that's a lot of that is about where our coastline is sort of more bedrock and cliffs versus marshes versus bluffs versus barrier beaches. And a lot of that kind of heterogeneity is a legacy of glaciers.
Yeah, for sure.
Where they plowed up sediment and left it.
Yes. Well, here's a good question, sort of related, from Doug, who's curious. So, I mean, obviously you're talking about the Gulf of Maine here largely, but how does, say, like Portland compare with the rest of the coastal US in terms of sea level rise, flooding potential? I'm assuming there are probably some other vulnerable locations across the US and elsewhere.
Yeah. Again, this is a complex question that I could sort of answer in a lot of ways, but maybe one interesting thing to point out is in Portland, we're particularly vulnerable in areas that were built on fill. So if you look at Portland's original coastline, and same is true for Boston and a lot of other coastal cities. Boston's maybe one of the most dramatic examples. The original coastline's a lot smaller. And back starting like 200 years ago, we started building revetments in the water and dumping fill in them and creating wharfs and building on top of them. And those are all areas that used to be intertidal areas. And So they're low lying, and fill also compacts under its own weight over time. So they're low lying and they're sinking as sea level is rising. So those are the areas in Portland that are the most vulnerable, and in Boston. Yeah, I'll leave it there.
And in comparison to say like, I guess I feel like Miami is usually one of those, especially metropolitan areas in the US, that's usually cited as like low-lying coastal location in the US that is pretty vulnerable to sea level rise. Is that true?
Yeah, right. I forgot about the larger context. Yeah, so we have quite a bit of topography in the northeastern US. So there's just like, yeah, things just get steeper along the coast. So floods impact a smaller area. Whereas, yeah, in Miami, it's like big low-lying areas with a lot of development. Same in Charleston, South Carolina, same in like throughout the Texas coastline. So I'd say compared to the Southeast and particularly the Gulf of Mexico coastline, we are far more resilient to flooding.
Awesome. Well, and speaking of resilient, Betsy asked a really good question. I know you mentioned sort of the end goal of some of your work ultimately, helps it advise communities specifically, what are they going to do? What are some solutions ultimate? Well, what is the information that they can consider to ultimately what sort of solutions might be put in place to combat sea level rise or coastal flooding or things like that? How involved, or how are you involved in maybe any of those recommendations, and what are, maybe if you can give an example or something of some of the ways in which some certain solutions or actions that maybe some cities are taking to combat flooding issues?
Yeah, maybe I'll give a couple examples. So one is that GMRI purchased Union Wharf, which is sort of to preserve it as working waterfront. And so I've been involved in coming up with a flood adaptation strategy for the wharf. And so these solutions are really, really localized. So for example, in working waterfront, first floors are often designed to be floodable. Like if you're processing lobsters there, they're corroding from the inside because of salt water. So we found that really the key thing to do was go and look at utilities and say, like, this furnace will be flooded in this year. And so let's look into replacing it with a heat pump in Y year. And so partnering with an economist in our organization to do a cost benefit analysis there. In terms of working with broader communities, there are, I have two counterparts within my team at GMRI, one who's a sort of community and municipal engagement specialist, and one who does sort of the same thing in the private sector. And we're soon going to be hiring a climate finance specialist. So the idea is that kind of within our team, I can say, here's what the hazard is. And then there are other people who can say, like, here's what our community wants and needs. And then someone else can say, here's how you access the financing to build a living shoreline to reduce wave energy from storms, or to restore a dune that protects from coastal flooding, or to maybe like buy out some properties to create a corridor for marsh migration, that sort of stuff.
Wow, fascinating. Yeah, I mean, certainly there are a lot of different ways I guess you can go about it, and depending on the environment and maybe some of the economics at play, there are a lot of different options at disposal. That's good, at least. Question here from Andreas, who's wondering if your research is shared with NOAA. If yes, do you receive any sort of financial support from NOAA, or just generally? I mean, I'm sure there's some level of relationship and connection with your work with that oceanic organization.
Yeah, my time's in part funded by a NOAA grant right now. And in my short time at GMRI so far, I don't have funded collaborations yet with NOAA researchers, but certainly talk with them on the phone a lot.
Yeah, and I'm sure a lot of other overlaps of the organization with, fisheries and all sorts of other things, I bet. Lots of wonderful comments, people very appreciative of your presentation this evening, and some other great questions as well. I'm sorry if I'm skipping over people's questions here, trying my best. And selfishly, I'm going to ask one of my questions as well, because maybe other people are curious about this too. You mentioned really briefly some of the technology you're using, some of the instrumentation. There are a bunch of people here who love instrumentation and geeking out on some of that stuff. What's some of the instrumentation that you're using to, I guess, some of the data that you're typically looking at? What are you getting into these days?
Yeah, so on the one part of my life is computer modeling. So, but when I'm not in the modeling world, one thing, mostly I work with water level data, and there are a few different ways to measure water level. One is with simple pressure transducers. So you can put basically just a little device that measures pressure underwater, put one above water to correct for atmospheric pressure and get water level measurements that way. And the ones that NOAA uses, so the long-term tide gauge stations they install, they're really expensive to install and maintain, something like $500,000. So there are not many of them. And in Maine, we have, depending on how you count it, I think 5,000 miles of coastline and just a few long-term tide gauges, and a pretty complex coastline with different physical processes, making tides and flooding look different everywhere. And so there are some new companies just kind of piloting these new low cost technologies that are more on the order of a couple $1,000s. And okay, how they work is something I'm still learning about. One of them uses, I think, microwaves to basically, you're just putting a sensor above the water and bouncing a signal off of the water surface, and a sensor is figuring out how long it takes to get back. But yeah, I guess what I really do is take the data out of them and then use that to generate tide predictions and do a bunch of statistics to figure out, to try to quantify flood risk.
Interesting. And I'd have to ask from a meteorological perspective, I mean, either yourself or some of your colleagues, what do you find, what sort of meteorological data are you most interested in or typically working with? I mean, some of your work is from a long-term climatological perspective, but some of it, like you referenced some of these more like case studies, like a singular weather event and sort of unpacking what happened in a storm. So I'm just kind of curious, especially for some of our listeners here, what sort of weather data you're looking at.
Honestly, I don't work with weather data much. The sort of extent of it is trying to figure out whether to characterize a storm as a tropical cyclone or an extratropical cyclone, because that impacts the way you calculate flood statistics, which is a boring rabbit hole we don't need to dive into. But yeah, I mean, honestly, I don't use it much. Mostly to check the weather for my non-work hour adventures, honestly.
Well, that's good. All right. Well, I thought we practiced this answer before the program. No, of course you use weather data all the time. Yeah, I mean, there's a question, and apologies, I lost the name already, around, trying to find, well, what are the connections between what's going on top of Mount Washington and the Gulf of Maine? Here we are, two institutions sort of meeting just for a moment. And yeah, at any rate, obviously we live in the same system here. One doesn't happen without the other. And it's always interesting to see when different sciences, I mean, very similar sciences, but different parts of the climate system come to meet here and what that ultimately means.
Yeah. And honestly, I think I guess sort of with anything you do, sometimes the farther along you get, the more narrow your scope gets as you really start to focus on something. But there are certainly people who have a foot in the coastal flooding world and the meteorological world. I just don't happen to be one of them.
Well, you must look at buoy data.
Yes, for waves.
There we go. For waves, at least. And they have some meteorological equipment there too. Anywho, that's all right. I'm not going to force that on you anymore. All right, let's see. Maybe time for just one or two more questions here, being considerate of everyone's time. Wow, yeah, a lot of wonderful compliments. Thanks everyone for sharing the kind words. Hannah gave a wonderful presentation tonight. So much information. Oh, geez, that's a lot of questions. Well, here's a good one. Someone's curious if you can provide your email address for any further questions, or at least I'm happy to say any follow-up questions. There'll be a follow-up email in which you're welcome to reply, or you can reach out to education@mountwashington.org. And Hannah, for more information, what's the best way to either learn more about your work or the work of your organization?
Yeah, please feel free to reach out to me over email. It's hbaranes@gmri.org. But if you just Google Hannah Baranes, Gulf of Maine Research Institute, my email will pop up there as well. And yeah, please feel free.
Awesome. All right, well, why don't we leave it there? Apologies if I didn't get to your question this evening. And again, for those questions that came in on Facebook, we'll certainly get to those questions as soon as we can. And I'm sure Hannah will be more than happy to answer a couple questions if they come following the program here. So thank you so much, Hannah. I really appreciate you giving your time this evening to present. Loved it, loved it, loved it. And for those of you who joined this evening, thanks so much for joining. If you enjoyed it, please consider making a donation to support programs like these over at mountwashington.org. You can hit the donate button that's in the upper right-hand corner of the website there. And don't forget, any donation in any amount also makes you a member of Mount Washington Observatory. If you have any thoughts about tonight's program or suggestions for future programs, please take some time to fill out our Google Form survey that will show up in the Zoom window that follows the program and also in our follow-up email. And finally, don't forget to join us next month on Tuesday, October 11th, when Mount Washington Observatory's Dr. Peter Crane will join us to help us celebrate the observatory's 90th anniversary. And he's going to join us to give a nice historic overview, some highlights of the organization over time. We're also going to make sure to set aside a lot of time for questions from all of our participants, an opportunity for you to share your favorite memories and stories about Mount Washington and the observatory. So make sure you check out that program. You can register for that program and also check out any of our previous programs over at mountwashington.org/SITM. All righty. Well, thank you so much again, Hannah. I really appreciate it. Hope you have a great night, and thanks everyone for joining. Take care.
Thanks again, everybody. Bye-bye.
Bye.